We're going to use Lewis dot structures to examine covalent bonds. Covalent bonds exist when we have shared electron pairs between the two nuclei. We find this in bonds between nonmetals with nonmetals. And the electrons are spending most of the time between the two nuclei. So that means the electron density is highest between the two nuclei. And this is what holds the two nuclei together, the attractive electrostatic attraction between the electrons and the individual nuclei. For Lewis dot structures, this is a simple process that's going to give us a lot of information. So for compounds, we're first going to add up all the valence electrons. If we have a polyatomic ion, where we have a charge, positive or negative, we're going to add the charge, add the number of electrons of the negative charge, or we're going to subtract the number of electrons from the positive charge. So we want the total number of valence electrons. We're not going to worry about where the electrons come from, what atoms electrons come from in this process. Now we have to lay out the atoms in an appropriate fashion. Typically, the first element of the formula is going to be this central atom. However, this is never hydrogen. Hydrogen only has one bond at a time, so it can never be a central atom. And for formulas that have 3 atoms only, the formula usually shows the layout of those. So we're going to put down the central atom, we're going to put down the other atoms around it. Now we're going to connect each bonding pair, that means all the surrounding atoms are bonded to the central atom, with a single line. This single line represents 2 electrons, a pair of electrons. We're going to add the remaining electrons that we have using dots as pairs on the atoms that do not yet have a complete octet, until we use up all our electrons. If we have excess electrons, we've completed the octet and everything, but we still have 1 or 2 pairs of electrons left. This should only occur if we have a period 3 element or higher as the central atom. We're going to put those excess electrons on the central atom, allowing that atom to exceed the octet. If after we put down all our electrons, we don't have complete octets on everything, now we're going to start moving non-bonding electron pairs into bonds, which will form double or triple bonds until we have complete octets. So if an atom does not have is short, does not have a complete octet, we reach to an adjacent atom, pull a non-bonding pair off of that into the bond between those 2 atoms. That'll create a double bond for the first time that you do it, a triple bond for the second time that you do it. But by doing that, the atom that you were taking the lone pair from does not lose it because you keep it in the bond. But then the adjacent atom that was short now gets to count those electrons, and hopefully we have a complete octet. When we have an odd number of electrons, then we cannot have a complete octet if we have an odd number of electrons. What we want to do is make the more electronegative element to have a complete octet, and the less electronegative element, or more electropositive element, will be short by 1 electron. So the less electronegative element will get only 7 electrons. So we're going to have a couple exceptions to the octet rule. So secondary elements, carbon through fluorine, we expect to always obey the octet rule. Boron is an odd element. It seems to like to have only 3 pairs of electrons. So often will complete itself with 3 pairs of electrons and not go for the octet. Beryllium, starting off with 2 electrons, will often lose those 2 electrons to form a +2 charge and have only 2 valence electrons, which will match helium at that point. hydrogen only gets 2 electrons, which will also match helium. We call that the duet rule for hydrogen. To have more than 8 valence electrons, we have to have a third row element or higher, fourth row, fifth row. These elements have the d subshell available, so we need the d subshell available to exceed the octet. So we can only have an exceeding excess electrons if we are third row, third period, or higher on the periodic table. So since the second row elements, carbon, nitrogen, oxygen, fluorine, do not have access to the d orbitals, these elements can never exceed the octet. If we have only one pair of electrons in our bond, we have a single bond. If we have 2 pairs of electrons in a bond, we have a double bond. If we have 3 pairs of electrons in the bond, we have a triple bond. The bond lengths listed here we don't have to memorize, but what we want to know is that as we increase the number of electron pairs in a bond, the bond gets shorter and stronger. So bond lengths get shorter and stronger as you go from single to double, double to triple. Sometimes we can write more than one valid Lewis dot structure for a molecule. When we can write more than one valid Lewis dot structure, the molecule really can resonate between those structures. We have 2 types of valid Lewis dot structures. Some are equivalent in terms of if we rotate the molecule, it looks identical to the original molecule. And some are non-equivalent, where there's a definite difference between the molecules. In a moment, we'll learn a process that will allow us to determine what is the best non-equivalent resonance structure. Of the equivalent resonance structures, we're just going to be resonating between all those types of structures. We have one special molecule, it's the beginning of a class of cyclic organic hydrocarbons or aromatic hydrocarbons called benzene, C6H6. It's a ring structure with 6 carbons forming a ring and a hydrogen on each of the 6 structures. We're going to be coming back to this a couple times. It's a special molecule, beginning of large class of compounds. This 6-member ring we could draw with 3 double bonds and 3 single bonds. There are 2 equivalent Lewis structures where the double bonds and single bonds switch positions. So the molecule really resonates between those 2 positions, so we end up with 6 identical bonds that are intermediate between the single and double bonds. And we will represent this later on as a delocalized bond, where the electrons really are moving around the whole ring structure. When we have non-equivalent resonance structures, we can decide which is the best resonance structure by using the process of formal charge. So formal charge lets us know the best of several non-equivalent resonance structures. And formal charge is the difference between the number of valence electrons on the original atom and the number of valence electrons assigned to it in the molecule. So the way that we assign electrons in molecules is that the atom gets all of the non-bonding electrons that it has, all the lone pairs that it has. but the bonding electrons are shared between atoms, so it only gets half of those bonding electrons. So formal charge is going to be the number of valence electrons on the original atom minus all of the non-bonding electrons and minus half of the bonding electrons. So we calculate formal charge for each atom in a molecule. Once we have all the formal charges of the atom, now we can use that to determine which is the best Lewis structure. One of the rules to show that you calculated formal charges correctly is that as we add the formal charges up for all the atoms of the compound, they must equal the charge of the overall species. So if we have a neutral compound, all the formal charges have to add up to 0. If we have a polyatomic ion, all the formal charges must add up to equal the charge of the polyatomic ion. To pick the best Lewis structure, we're going to pick the Lewis structure that has the values closest to 0. So if you do the sum of the absolute values, you want that value to be the closest to 0. So if all the formal charges are 0, that would be the best Lewis structure. But otherwise, we sum the absolute values to see which is closest to 0. Now if we have some with the same equivalence in terms of being closest to 0, we also want any negative formal charges to show up on the most electronegative atoms. So we don't want negative formal charges on the lesser electronegative atoms. We want the formal charges to be, the negative formal charges to be on the negative, most electronegative atom in the molecule. So, to do a formal charge of boron trifluoride, we can draw this structure with 3 single bonds that will leave the boron with an incomplete octet. Or we can draw it with a double bond, which will give a complete octet on the boron. So, we can check to see which one's better. So if we have 3 single bonds, if we have 3 single bonds, for fluorine, we're going to start off with the 7 valence electrons for fluorine. It's going to have 3 lone pairs, so 6 lone pair electrons, and we're going to give 1 of the bonding electrons to the boron. So that will be 6 plus 1 is 7. So we have 7 valence electrons minus 7 assigned electrons will give us a charge of 0. And that will be the same for all 3 fluorines. For the boron has 3 valence electrons originally. In this case, we'll have 3 bonds. We're going to assign 1 electron from each bond to the boron, so that's total 3 electrons. So we have 3 valence electrons minus 3 assigned electrons for 0 formal charge. So if we have a double bond, if one of the fluorines has a double bond on it, for the fluorine to single bond, it's going to be the same as before. 7 valence electrons minus 7 assigned electrons will equal 0. For the double bonded fluorine, we're going to have 7 valence electrons. This fluorine will only have 2 lone pairs, so that'll be 4 electrons. It's going to have a double bond, so we have 1 electron from each of those double bonds. So 4 electrons from the lone pairs plus 2 from the bonds will give us 6. So we have 7 minus 6 is a formal charge of 1 on that fluorine. For boron, we have our 3 assigned electrons. Now we have 2 single and 1 double bonds, so a total of 8 bonding electrons. We're going to give half of that, 4, to the boron. So we're going to have 3 valence electrons minus 4 sign electrons equals negative 1. So when we compare these, on the 3 single bonds, we get 0 formal charge for both fluorine and boron. So this is the best charge. Since with the double bond, we're going to have 1 fluorine with a negative, 1 fluorine with a positive 1, 1 boron with a negative 1. So the sum of the absolute value is going to be 2, not 0. So the 3 single bonds is better in that regard. Also, down here with the boron with a double bond, we got the positive charge on the fluorine, negative 1 charge on the boron. But this reverses the charge. We really want our negative charge to be on the more electronegative element fluorine, but instead it's on the more positive element boron. So that also is a bad combination for formal charge. So boron trifluoride has the best structure with 3 single bonds, which is what we find in nature. So the formal charge process gives us the correct structure for this compound.